our exam, and I hope that you will all do well on it. I'll start the lecture today by going to looking at the different fission systems and the different nuclear reactor designs. Remember that we covered the topic of producing power from radioactive isotopes. We also suggested that geothermal energy has its origin in the radioactivity existing in the Earth's crust, but humans have discovered the process of fission, and for a while they thought that they have discovered something that didn't exist in nature. We'll see later that in fact it did happen in nature 2 billion years ago. So we start here on our chapter on the nuclear reactor concepts and the different thermodynamic cycles, and we will cover as many of the reactor concepts, both existing and operating all over the world, as well as the different concepts that are on the drawing boards and even ideas that haven't been pursued yet. Nuclear fission reactor shares the same basic design in that they have a core, very similar in terms of components as the Chicago pile number 1 that we covered in our first 2 lectures. You need a core that contains a fuel, in that case uranium, primarily the uranium-235 isotope that can fission. And then you need a moderator. The Chicago pile number 1 had graphite, which is carbon-12, the isotope of carbon, as a moderator, and that helps reduce the energy of the neutron from the 2 million electron volt at which they are born in the fission process, all the way to a thermal equilibrium with the moderator medium. In that case, for most of the existing reactors in operation today, it is water, plain water, H2O, but some designs, as we'll see, also use heavy water. So in that case, the one of the atoms of, or 2 of the atoms of hydrogen in water is replaced by the heavy isotope of deuterium. So it's D2O or HGO as the coolant. Nuclear power plants differ from fossil fuel power plants like coal or oil based or natural gas, even gas turbine plants, in that they are closed systems. There is nothing that is released unless you have an accident in terms of the products of the fission process, or that is in contrast to fossil fuel power plants like coal power plants produce so much products of combustion that they cannot be contained. So how do we dispose of them? Basically, we dilute them into the atmosphere, as we know. A coal power plant, a fossil fuel power plant, requires a huge input every day of the fuel. So you need basically, for a typical 1,000 megawatt electric coal plant, a train load of about 100 cars of coal daily. Nuclear power plants would be refueled every year to even a year and a half. And that has to do with the very high specific volume or specific energy or energy per unit mass, as well as the high energy density of nuclear fuel. We do not allow radioactivity to be released in the environment. In the case of nuclear power plants, we contain it. And then in the same way that we mine uranium out of the ground, we dispose of that waste back into the ground. Fission energy, basically, that is released in the fission process is initially the kinetic energy of the 2 fission products. When the uranium-235 nucleus splits into 2, these fission products repel each other through the electrostatic repulsion, the Coulomb force, in fact. And as they lose their kinetic energy by colliding with the surrounding medium, that kinetic energy is converted into molecular vibrations, which is heat. So when you produce a fission energy, you need to cool the fuel, and in that case, the water, which is a moderator in existing power plants, also acts as a coolant. So the coolant acts doubly as a moderator and as a coolant. And it uses the energy from the 2 million electron volt of neutrons born in fission to the 0.025 electron volt, which we named earlier the KT neutrons, K being the Boltzmann constant and T the Kelvins. You equip a nuclear power plant with a neutron reflector, which is a material that has a low Z or low atomic number, and to reflect some of the neutrons back into the core instead of having them leak out of the system. And the heat from the coolant is moved to heat transfer cycle, where eventually electricity or process heat for other applications, such as desalting seawater. Like if you evaporate seawater, you obtain fresh water. And in fact, the world has a shortage today of freshwater supplies rather than energy as electricity. You could use that heat also in other processes like hydrogen production. Hydrogen production would come in from the splitting of the water molecule into hydrogen and oxygen. And in that case, what you get is hydrogen that you can store, and you can also use it in a transportation system of the future that would be based on fuel cells rather than the ICE or the internal combustion engines. And you can also produce district heat, like replacing our coal power plant on campus by a nuclear power plant would save lots of disease spreading all over town, as well as from the products of combustion and the pollution and over the campus, in fact. Safety systems are incorporated into the design to provide safety to the operators and members of the public. Along this line, you'll find that the laws of thermodynamics apply, but here we are really interested in energy conversion. And in energy conversion, we can extract energy from the environment and convert it from one form to another. There are some general principles. Of course, the laws of thermodynamics apply to thermal systems, but we don't use only thermal systems to produce electricity. We use also hydrodynamic systems in when you use hydroelectric power generation, and we use aerodynamic energy also when you use the wind to produce energy. So some general principles apply for us as engineers to extract energy from the environment. And if the energy available to us is a natural process, we adopt it. Otherwise, we create systems that would extract energy from the environment. Some general principles apply when you consider the energy conversion in general. And it does not conflict with the laws of thermodynamics, especially for thermal systems. A first basic principle is that you can only extract energy from the environment if you have a flow system, like a stagnant system, like water behind a dam does not produce energy for you. Even the fuel like gasoline in the tank of a car, if you do not flow the gasoline into the engine, will be simply stored energy. It cannot produce energy for you. So in general, when we want to produce energy or convert it from one form to another, we must find a way of creating a flow system. And a corollary of that principle is that the energy has to flow from a high energy storage reservoir to a low energy sink. So if you have water stored behind the dam, it cannot produce energy. Once you allow it to flow, so you establish a flow system, then it has to be from a stored energy in the form of potential energy, MGH, behind the water behind the dam, and into a sink, which would be the turbines that rotate to produce electricity. So in hydroelectric power generation, the potential energy of water blocked behind the dam or a waterfall or a river stream, you cannot extract the energy unless you allow it to flow. If you don't allow the water to flow, it's obvious you cannot produce or extract energy. In a heat engine, on the other hand, you'll find that the energy cannot be extracted from a totally insulated reservoir. You have to allow the heat, in that case, to flow from the high temperature reservoir at which heat is added to a low temperature reservoir where it is rejected to the environment. And basically, if you don't do this, you cannot extract energy from the environment. And notice that energy in the environment is very ample. It's all over around us. It's our task or duty as engineers to extract it for the benefit of society according to what society wants us to do. If you consider geothermal energy production, you'll find that you are using the differential temperature deep underground, close to the magma and the earth surface, and between it and the earth surface, so that you allow energy to flow. In ocean thermal energy production, OTEC, the cooler temperature would be at the bottom of the ocean, and you basically circulate a low boiling point medium like ammonia from the cool temperature at the bottom of the ocean to the top where water is warm. So you can use ammonia, for instance, in that system. It doesn't have to be water. Totally blocking a wind stream, like if you build a wind turbine with a very large number of rotor blades, would not allow you to extract energy from the wind. You must allow some of the wind to flow in between the rotor blades. Hence, you see wind turbines having 3 large rotor blades. If you put in a large number, it is not even optimal in that case. And in that case, what you allow in wind power production, which is an aerodynamic system, you slow down the wind. You break part of the wind from the front upwind of the wind turbine and break the wind to a lower speed on the downwind part of it. And in between, you extract some of the energy as mechanical rotation of the rotor blades and then electricity in an electric generator. So allowing a flow system to occur definitely is a must for energy conversion from one form to another in the environment. We can state the second principle is that you can only do that extraction of energy if you have an asymmetry. And you must have the asymmetry in a hydraulic system. It could be kinetic, it could be thermodynamic or aerodynamic. Basically, that asymmetry allows you only to extract a portion of the available energy in the system. And ingenious devices built and designed and operated by engineers. You see, ingenious and engineers some kind have the same etymology here. Conceptualized by ingenious people, take advantage either of naturally existing asymmetries or alternatively, you create artificial configurations. That's a trick here on how you can extract energy from the environment. And if you find that you have a natural kind of asymmetry, like a waterfall, Niagara Falls, you use it. If there isn't a natural asymmetry, you create it. And when you create it, like you build the dam in that case, store energy in the water and then allow it to flow, then you can extract energy from the environment. So these are two basic principles. First, you must have a flow system, and the flow system requires to use either a natural or a man-made asymmetry. Along this line, a third principle applies. If you have a flow system, that necessitates that only a fraction of the available energy has to be extracted. And in that case, we define an efficiency that is characteristic of the energy conversion process. And you extract as much energy from the flow system as you can, and the rest is left back to the environment. And in fact, it is used to establish the flow system, whether it's heat in thermodynamics systems or in the form of flow of the water, say in a hydraulic system for in the front of a dam. So in that case, the efficiency basically is the energy that we can extract, the fraction of energy that we can extract from the flow system, and the rest have to be returned back to the environment in one form to the other. then we can have, in that case, a corollary to that third principle. You'll find that the conversion efficiency is proportional to the width of the existing or the created artificial asymmetry. So if you have a waterfall that's very high, then of course you find that you can extract more energy from the process. In that case, the width of the existing natural, or the delta T in thermodynamic system, if you create, of course, an artificial asymmetry. You'll find that conversion efficiencies differ from one energy conversion system to another. For instance, in thermodynamic, the ideal heat cycle efficiency is expressed by the Carnot cycle efficiency. However, if you deal with a wind stream producing electricity from it, there is also an associated efficiency, but it is described by the Betz equation. And you can go and read about it in our course on wind power systems in general. If you talk about nuclear energies, you find that we are using different thermodynamic processes, and the different thermodynamic processes, that's when we concentrate on nuclear energy, it's a thermal process. You'll find that that defines different reactor concept. Notice again that those energy conversion principles do not conflict in any way with the laws of thermodynamics. The laws of thermodynamics apply to all energy conversion systems. They control interactions of everything in the universe, regardless of scale, and these rules stretch across every form of science known to humanity. The word thermodynamics comes from two root words, thermi, meaning heat in Greek, and dynamis, meaning power, implying that the laws of thermodynamics are the laws of heat power. Even if you think about the wind flows because of a differential in temperature from one part of the Earth to another. The Zeroth Law of Thermodynamics says when two systems are each in thermal equilibrium with a third system, the first two systems are in thermal equilibrium with each other. And that's what we call the Zeroth Law of Thermodynamics. To be able to measure a temperature, thermal equilibrium must be reached between the thermometer as a whole and the mercury inside the thermometer and the substance being whose temperature we are measuring. This results in being able to accurately tell what the temperature of a substance is. The first law of thermodynamics is also called the law of conservation of energy. We're going to apply it several in different instances in our class. Energy basically cannot be created or destroyed in an isolated system. The change in a system internal energy is equal to the difference between the heat added to the system from its surroundings and the work done by the system on its surroundings. So that first law addresses the interconvertibility of work and heat as forms of energy. So we can define the internal energy du as equal to the heat dq plus dw, the incremental work done. From a different perspective, it states that matter and energy cannot be created, nor can it be destroyed. The quantity of matter and energy remains the same. It can change from solid to liquid to gas, plasma, and back again. But the total amount of matter / energy in the universe remains constant. As a second law of the thermodynamics states that all spontaneous processes produce an increase in the entropy of the universe. And in that case, we define the entropy ds of an isolated system as continuously increasing. And in that case, heat does not flow spontaneously from a colder region to a hotter region, or equivalently, heat at a given temperature cannot be converted entirely to work. So we define the entropy as being the change in the heat of a reversible system divided by T. And here I'll make a very important point is as engineers, when we see that symbol capital T, this is the kelvins. We don't call it anymore degrees Kelvin, we just call it the kelvins, which is 273 plus the degrees Celsius. So the room temperature, if you say the room temperature is 20 degrees Celsius, the kelvins is 273 plus 20. In that case, you'll find that the change in entropy is always larger than the change in the heat content in an irreversible system divided by the Kelvin, number of Kelvins. The third law of thermodynamics obviously states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. And it is part of the nature of the universe that the entropy increases, and only by reordering knowledge, for instance, what we are doing today, we are decreasing the entropy by increasing order. So you decrease the entropy only by increasing order. That means that you have to spend energy in that case. Coming back to nuclear power generations, you'll find that the different reactor designs that we can think of, and in fact, there could be as many designs of nuclear reactors as there are designers, provided you get some compatible set of fuel, moderator, coolant, and a control system. There are several different reactor concepts that we are going to try to study, but the differentiation between them depends on how much energy you are producing in a unit volume. So if we take actually here we are stating in terms of power, in terms of megawatts, which is millions of watts, and we are specifying here that is not watt electric, this is thermal watts. Still, it hasn't been converted into electricity. It will convert into electricity with an overall thermal efficiency. But if you take the power that you produce per cubic meter, or the power density, see, this is power megawatt per unit volume, that's power density, and we designate it as Q triple prime. That would be equal to the energy release in the fission process, our 200 million electron volt per fission event, multiplied into the product of two quantities that we are going to call here the neutron flux, or how many neutrons are crossing unit area per unit time, and then multiplied by the probability that they are going to cause a fission that releases that energy E sub F. So we designate this by what we are going to call the macroscopic fission cross-section. And when we take those two together, it gives us an indication of how many fissions are occurring per unit volume, and then you multiply it by the energy release per fission. That gives us the power, or the energy release per unit time per cubic meter. Different reactor concepts have different levels of that core power, average power density. We'll see that we have several reactor concepts, but I'm going to list 5 of them here. One uses water that is pressurized. You pressurize the water in the same way that you pressurize the coolant in the radiator of your car. The pressure on it basically does not allow it to boil at a higher pressure. So when you pressurize the water, you can operate at a higher temperature without the water boiling. We designate that type of a reactor as the pressurized water reactor, and the acronym for it is PWR. If you allow the water to boil, we have a different type of a reactor, and it's designated as a boiling water reactor. Obviously, if you don't boil the water inside the core of a reactor, you have to send the pressurized water into a steam generator, where steam now is produced by converting the heat that is generated in the reactor core to a stream of water in the steam generator. A boiling water reactor has a different volume than a pressurized water reactor, and that core power density, the Q triple prime that we mentioned earlier, is larger in a pressurized water reactor than it is in a boiling water reactor. And since you produce less heat per unit volume in a boiling water reactor, you find that the core volume in a boiling water reactor would be higher than in a pressurized water reactor. On the other hand, that pressurized water reactor has to be associated with a steam generator where the steam is going to be produced. These two types of reactors are also designated as LWR, L for light water reactors, LWR. They both use water. Why water? Water is very cheap, very much available. All its physical properties are known, and it's easy to manipulate just as a fluid in that case. We can also use a different type of a coolant. We can use a gas. And if you use a gas, you find that you use maybe graphite, the same as Chicago pile #1, as a moderator, and circulate a gas into it. The gas could be as simple as helium, the best choice in that case, or it could be plain carbon dioxide. The advantage of working or cooling a reactor with a gas is that you can reach much, much higher temperatures. Hence, the design is named the high temperature gas-cooled, of course, reactor. In that case, the average core power density is much lower than for using water, and the core volume would be definitely much larger accordingly for the same amount of energy that you produce. The high temperature gas-cooled reactors can use a moderator like graphite. Graphite is what we use in our pencils. It's not lead pencil, it's not lead, obviously, it's graphite. You can build a reactor that does not use a moderator. In that case, it's called the gas-cooled fast reactor. The neutrons, if there is no moderator, remain fast. And in that case, they allow us to do better the process of breeding, meaning that we can produce more fuel as the neutrons interact with the fuel material, the uranium-238, producing plutonium. And in fact, you can produce, in principle, more fuel than what you are consuming. Ideally, you can also think about for each nucleus of fissile material that you fission, you can produce a new fissile nucleus. So this is the dream or the unique feature of nuclear energy, is that if you design it along the line of breeding, almost like breeding livestock, you can produce as much energy or even more than what you are consuming. This is not adopted yet in existing reactors, but this is a vision for the long-term use of nuclear energy. You can cool the reactor with gas, like in the high temperature gas-cooled reactor, or the gas-cooled fast reactor, in which you can breed more fuel than what you consume. These two processes can reach very high temperatures, so they lend themselves to processes like producing hydrogen from thermochemical processes. And hydrogen is contemplated as a future fuel for a transportation system using fuel cells. In fact, hydrogen would act better for a longer and a larger energy storage. So it would lend itself more for instead of passenger cars, but more like for trucks or buses. That is being researched, and some of the fuel cell trucks are being really where you produce hydrogen at high temperature, and then you store it and use a fuel cell as the engine for a future transportation system. It's a vision of a new transportation system. You can use also a liquid metal to cool the reactor, like sodium or an alloy of potassium and sodium. We designate this as a liquid metal fast breeder reactor. And when you use that heavy elements, sodium, for instance, as a coolant, you do not moderate the neutrons. The neutrons do not come totally in thermal equilibrium with the medium. And those fast neutrons are able to provide us with the process of breeding. So this breeding type of a design uses fast neutrons, and in that case, breeding is allowed. If you go to the gas-cooled fast reactor, you find that your core power density increases dramatically. So the volume of the reactor would be lower than existing power plants. And again, with the liquid metal fast breeder, you get the highest core average power density, 530 megawatt per cubic meter. If you want to get an idea about the megawatt per cubic meter, the units are the same as watt per centimeter cube. So here in the pressurized water reactor, you are producing 70 watts per centimeter cube. Think about 1 centimeter cube, and in that centimeter cube, you produce the power that you get from a 75 watt bulb. If you go to the liquid metal fast breeder now, it is not 75 watts, but 570 watts produced in 1 centimeter cube. So the volume of the reactor would be much smaller, meaning that the capital cost is low, but this is countered by needing a more elaborate safety feature so that you can extract the heat efficiently from the core of the system. More detail about the choices of different reactor concepts that we are going to deal with is the power levels that we can reach. We can reach with a 3,000 megawatt thermal of power with, say, a conversion efficiency to electricity of 1/3. You can get 1,300 megawatt thermal in a BWR or a PWR. This is almost a standard size. However, if you look here in the last column about the efficiency that we can get from the light water reactors, the pressurized water reactor or the boiling water reactor, you find it is only in the range of 33% or 1/3. So 2/3 of the energy in that case, in that particular design, has to be dedicated to establishing what we call the flow systems. Not that we really have to throw energy to the environment. It's part of the design is that we have to dedicate 2/3 of the energy to establish the flow from the high temperature reservoir to the low temperature reservoir. Notice when you go to the high temperature gas cooled reactor, your efficiency increases to about 40%. The AGR is a design that was built in the UK. It's an acronym for Advanced Gas Cooled Reactor. And this type of reactor was cooled by carbon dioxide. The high temperature gas cooled reactor is contemplated to be cooled with helium. But notice because we use the graphite as a moderator, and here we use the sodium, which is not a good moderator. So in that case, the neutrons remain fast and they can achieve the process of breeding, producing more fissile fuel than what we consume, not double or triple, but maybe 25%. So the breeding ratio in that case would be 1.25 or 1.2. Notice again that going to a gas-cooled reactor increases our efficiency from the 1/3 to maybe the 40%. The gas-cooled fast breeder reactor also is in the range of the 36%. Helium would be used as a coolant. What are the properties of the fuels used in those different systems here? You'll find that the fuel loading in a pressurized water reactor would be in the range of 102 metric ton. Notice here, if you use the SI system of units, we use the ton, T-O-N-N-E-S. It is not the same as ton, T-O-N. I warn you about this. Many people in the engineering profession do not make that mistake. The ton can be the 2,200 pounds. That's a British system of units, or the American ton is different than the SI or System International system of units. That's a metric ton, which is 1,000 kilograms. All right, so this would be the heavy metal that you need to run a PWR or a boiling water reactor. To be able to use water as a coolant, you'll find that the neutrons that cause the fission in that type of a reactor are absorbed by the oxygen and the hydrogen in the water, by the oxygen particularly. And uranium in nature today has an enrichment of 0.72% in uranium-235. Yet this is the isotope that fissions. To build a significantly well-sized PWR or BWR, you need to increase the amount of uranium-235 in the fuel. So in those two types of reactors, we enrich the uranium to the about 3 to 5%. Same for the advanced gas-cooled reactor and the high-temperature gas-cooled reactor. If you go to the liquid metal fast breeder to make the core more compact, we increase the enrichment of the fuel uranium-235 to uranium-235 plus uranium-238 to the range of 12%. In research reactors, we increase the size to 20%. And for naval propulsion, we want a very, very compact core, also a core that can last for a long period of time. Maybe sometimes the lifetime of the core is only one refueling. Then in that case, you go to the 90% enrichment in general. The power density, as I suggested, of the PWR is higher than for the boiling water reactor, but you still lose on having needing a steam generator. Now we define here what we are going to call the breeding ratio. If you produce more fissile fuel than what you are consuming, you define this and call it the breeding ratio. And the liquid metal fast breeder can achieve a breeding ratio of 1.27, meaning that you produce 27% more fuel than the fuel that you have consumed. The gas-cooled fast breeder reactor uses now a mixture of uranium and plutonium because you breed from uranium, plutonium-239. Both of those systems, you find that you can achieve a breeding ratio of 1.4. The high temperature gas-cooled reactors have been associated with the use of the thorium as a fuel. In that case, you use the thorium, you absorb a neutron into it, and it converts into the uranium-235 isotope. You can also breed with thorium, but existing designs, at least for the PWR, BWR, and high temperature gas-cooled reactor, do not breed. We are not using breeders today because the cost of the price of uranium is very low. However, we cannot continue along this line. We have maybe a 50-year supply of uranium without going to the breeding process. When the breeding ratio is less than 1, we don't call it a breeding ratio anymore. We call it a conversion ratio. So existing pressurized water reactor and BWR, they do produce fissile fuel in the form of plutonium here, but the conversion ratio in that case is 0.60. You produce only 0.6 atoms or nuclei of your plutonium-239 and then burn it per atom of uranium-235 that you burn. So eventually, definitely, humanity, once the supplies of uranium-235 starts being depleted, has to switch to the breeding. And this is the vision in the long term of nuclear energy, in that it provides us with an unlimited energy supply, where if you make it one, basically a system would produce as much fuel as it burns. However, here we can also build systems that use breeding in nuclear energy, whether you use thorium, which is 4 times more abundant than uranium in the earth crust, or use uranium. In that case, we can produce 30%, up to 30% more fuel than we consume. So nuclear energy becomes an unlimited energy supply. When we build nuclear reactors, as I suggested, we build a closed system. Why? We cannot really allow the fission products, which are highly radioactive, to be spread in the environment. In contrast to fossil fuel power plants, because we produce so much of the carbon dioxide and the combustion products, sulfur dioxides and nitrogen oxides, what people call the SOxes and the NOxes, we cannot allow the dilution to the environment. So, and in fact, we can do this because the energy in the nucleus is much more concentrated, and we don't produce really much fission products, maybe the size of a desk for a 1,000 megawatt reactor of high energy fission products per year. So in that case, in the nuclear reactors differ from fossil fuel power plants in that we have a closed system, and to keep that radioactivity that comes out after the fissioning of uranium, we use a concept called the multiple barriers concept. First, you'll find that the fuel itself is an oxide of uranium. So you have UO2, and a ceramic, as we know, can take high temperatures, UO2, an oxide of uranium, as well as it is porous. Some of the gases that come out, so products that come out of fission are gases at the temperatures of operation. Like, for instance, you can think about xenon and krypton noble gases produced by fission. These are trapped inside the pores of the ceramic or the porous fuel. You place that fuel inside the metal fuel cladding, as we'll see in detail later on when we look at the different designs. The British name that cladding or a tube where the fuel is placed, they call it canning. So it acts as a can, basically. Then you place that metallic fuel inside a reactor vessel that is isolated from the environment. You surround the whole reactor system. I will look at designs pretty soon with a concrete shield to protect the plant operators against the emission of radiation in the form of gamma rays. Remember, we said that gamma rays can penetrate 1 meter of concrete. So you need to use lots of concrete to protect the personnel. And that is through what's called the containment structure. And we do not build nuclear power plants in highly populated areas. We get an exclusion area around them with a low population, and it creates a separation distance from the large population centers, so that if an accident occurs, for instance, in the case of Fukushima, Fukushima was far away from Tokyo, so the release of radioactivity did not reach Tokyo as a highly populated area in general. So to be able to achieve this, we equip our designs of nuclear power plants with what we call engineered safety features, which provide us against two sources of failure in the operation of nuclear power plants. It could be caused by human error. The 3 Mile Island accident was primarily caused, and Chernobyl, in fact, were caused by human error, but it could be also equipment failures. That was the case of Fukushima as a result of the earthquake and the tsunami. And in that case, of course, Fukushima also qualifies as a natural event. So let us look at how we equip our nuclear designs with these engineered safety features. And the goal here is not to allow under any circumstance the release of radioactivity to the environment, except when these accidents occur due to human error, natural events, or equipment failures. First of all, the first engineered safety feature is where we have the control rods. Once those control rods here, this is showing the pressurized water reactor concept. If they're inserted inside the core, they absorb the neutrons. The neutrons would be causing fission, so you stop the fission process. However, something unique to nuclear power plants is that even after you shut down the fission process by inserting the control rods, you'll find that the radioactivity in the fissioned fuel continues for a while, maybe 24 to 48 hours and a little longer. And it's very different than when you operate, say, a boiler in a coal power plant. Once you stop injecting the fuel into the boiler, the production of energy ceases. But in nuclear reactors, you'll find that those fission products continue emitting radiation in the form of beta particles and gamma radiation. Initially, at time t equals 0, after you shut down a nuclear reactor, you'll find that you are producing about 8% of the fission energy or power even after you shut it down. That radioactivity decays very rapidly, but if you do not extract that heat immediately after you shut down the fission reaction, then you can melt the core, 3 Mile Island, or cause great damage like at Fukushima as well as Chernobyl. If the control rods for some damage in the core cannot be inserted, you find that you use a safety feature of boric acid dissolved in water, stored in a tank. You inject it into the core, And the boron is a very strong absorber for neutrons, so it would replace your control rods. So a second engineer safety feature other than the control rods is the boron injection tank. And as we need to cool the reactor even after you shut it down for at least 24 hours, you'll find that you have a supply of extra water here. For the pressurized water reactor, it's a tank that is under pressure by nitrogen pressure. These are called the accumulator tanks. In case the pump fails, say from an earthquake, or there is a leakage in some of the piping, the coolant that goes through the reactor pours through to a steam generator, or steam is being produced. In that case, once the pressure is decreased below 20 atmospheres, you'll find that that nitrogen pressure automatically injects its water into the core to cool it. So this is basically an excess supply of water on land-based systems. If you have submarines out in the ocean, well, you have the whole ocean to cool the reactor. Another source of extra supply of water is the refueling water storage tank. So if for some reason some of that piping is damaged by possibly an earthquake, then that water is brought in and pumped into the core. Initially, the pressurized water reactor operates at a very high pressure, about 2,000 pounds per square inch. So if you want to inject water in an accident condition into the system, you have to provide pumps that generate very high pressure. So we have a coolant system that uses pumps that generate high pressure, and that's what we call the HIPSI, HPIS system, or a high pressure injection system. Now, if you have a pump that generates high pressure, you'll find that it generates also a very low throughput in the flow itself, and you inject that into the core to cool it if there is an accident. However, the flow rate is very low when you produce high pressure. So in that case, the operator would either depressurize the system intentionally, or the accident itself, if say that pipe breaks down, would depressurize itself. Then you switch to a low pressure coolant injection system that goes through what is called the residual heat removal system. Each X here stands for heat exchanger at each X. If you get a breakage in the piping, steam would be released. So the refueling water storage tank becomes a source of water where you spray inside the containment. The containment is a steel shell. The steel shell is surrounded in the design by concrete. The concrete really is for the protection of the internals of the reactor against a direct impact from a 747 airplane, but the steel shell is there to condense any steam that would be generated inside the reactor. Now, as that containment spray operates, the water accumulates in a sump, and the water from there is pumped to that residual heat generator, and the heat is rejected to the environment from the steam generator. So in that case, you find that all these features are there to protect land-based reactors. Notice that the size of those reactors is determined by the enrichment. When we went to higher enrichment, say in the liquid metal fast breeder, the core volume was lower. Why is it 3 to 5%? It's totally arbitrary. When they started building nuclear propulsion systems for submarines, they started using very highly enriched fuel to make a very compact core that can also last for a long time, and for overcoming what's called the xenon dead time of the reactor. So the person in charge of the whole process didn't want to have highly enriched fuel circulating around 90% enrichment in uranium-235, which is suitable for naval propulsion reactors, but also can be used to make weapons. So he came up with an arbitrary value, 3 to 5% for land-based reactors, and it stuck. So we have really a very highly disadvantaged system just based on a criterion that does not really apply today. So here is a list then of the engineered safety features, or ESFs, for the PWR: the control rods, the containment vessel, the accumulator tanks, the residual heat removal system, the high pressure coolant injection system, the low pressure coolant injection system, the boron injection tank, and also the water in the refueling water storage tank. In the pressurized water reactors, as we see in that diagram, we do not allow the water to boil inside the core by an extra piece of equipment that we'll study later. It's called the pressurizer. So the water does not boil inside the core. It boils and produces steam in a steam generator right there. And the steam goes to the turbine part of the plant where electricity is produced. Then it is condensed in the condenser like a conventional power plant. And the water, the mean feed water, is returned back to the steam generator. If you allow the water to boil inside the core, you don't need the steam generator and you don't need the pressurizer. And the economics really are some kind of similar, but when you go to a boiling water reactor, you'll find that most of the engineered safety features still are used in the same way as a pressurized water reactor, the PWR. However, there are some differences. For instance, as you produce the steam, you need at the top of the reactor core steam drying equipment. You don't want to send to the turbine steam that is carrying droplets of water, because the blades of the turbine generator tied to electrical generator, the tip of it is almost moving at the speed of sound. So if you have droplets of water, you would cause erosion. So you have lots of drying equipment on the top of the core. So you cannot bring in really the control rods from the top, like in the PWR. See here, the pressurized water reactor, the control rods come from the top. For the boiling water reactor, because of the existence of the steam drying equipment at the top, they come in usually from the bottom of the core. Also, the core, the pressurized water reactor, is equipped with a feature that does not exist in the pressurized water reactor, is that you have a large supply of water in the form of a torus here. At the bottom, it's called the pressure suppression pool. If any of the piping breaks, steam is released. It is bubbled out in that water in the pressure suppression pool. And in that case, this is also a source of cooling water. The water goes through a heat exchanger and is pumped into the core to cool it in the case of an accident. And then you also have a core spray system that takes water from that pressure suppression pool and sprays the core in case there is a loss of coolant. The main worry here is an earthquake breaking the coolant lines. The boron injection also is a feature same as a pressurized water reactor. There are no accumulators, but you have the condensate storage tank to replace the accumulator tanks in the pressurized water reactor. And you still also have a high pressure coolant injection system. Once the system is depressurized, either intentionally by the operator or the system basically loses so much coolant that it is depressurized, and you start running through the heat exchanger here, the low pressure coolant injection system. As I suggested, a high pressure coolant injection system would operate with a low throughput, a low level of mass flow rate. When the system is depressurized, you can have a low pressure coolant injection with a large throughput and cooling effect. So we can list the engineered safety features, or the ESFs, or the boiling water reactor. Same as a PWR, the control rods, the containment spray system, the pressure suppression pool is a feature of the BWR. The residual heat removal, same as a PWR. Same as a PWR, a high pressure coolant injection and low pressure coolant injection, a boron injection tank, and the excess supply of water is not the refueling storage tank or the accumulator tanks, but condensate storage tank. And typical of the BWR also is an internal core spray system. So you could see here that we have several layers of defense against any kind of failure that can happen in either designs that are in operation today. What kind of fuel cycles do we use? As we suggested, when you use water, you use what we call the Rankine steam cycle. Or the steam cycle is also named the Joule steam cycle. Depends whether you live in France, you call it the Joule cycle, but in general, it uses steam. So in a steam, you evaporate the water by adding heat and adding latent heat of vaporization. This is on what we are going to call the TS diagram, temperature against entropy. Once you reach the saturation line for the water, you can superheat it, send it to a turbine, expand it in a turbine, then reheat it again and expand it back in the turbine. Once the steam has done its work in rotating the blades of a turbine and the blades of an electrical generator, you condense the steam in a condenser by rejecting some of the heat to a cold reservoir. So in that case, you have now the flow system between the high temperature reservoir at about 500 to 1,000 degrees Fahrenheit to the environment. In that case, it could be cooling lake, like at the Clinton plant west of town, 45 miles west of town here, or you can use the cooling towers. Once you condense the water, you send it through feed water heaters. You can increase the efficiency of the system by bleeding some steam from the turbine and heating it. And then you send it through an economizer and then to an evaporator. You can notice here that the Rankine or the steam turbine cycle reaches temperatures in the range of the 500 to 1,000 degrees Fahrenheit. However, if you really want to reach higher temperatures, and we suggested that that would be associated with the, in that case, an increase in efficiency from 30% maybe to 40%, then you use a gas turbine cycle or what's called the Brayton cycle. That's a terminology in the UK. In that case, you use a gas. You heat up the gas like carbon dioxide or helium, and you can reach here about 1,500 degrees Fahrenheit. So that would be a higher efficiency type of a reactor. And also you can use thermochemical processes that are, or high temperature electrolysis to produce hydrogen, which is contemplated as a future energy carrier or energy storage medium for future transportation systems. So when we are going to run out of the fossil fuels, that would be nuclear energy, wind energy, geothermal energy, hydroelectric plants to produce hydrogen. So in that case, you heat up the helium or the carbon dioxide, the gas, expand it in a turbine. Then you try to recuperate some of that heat. So you reject the heat from one side as the coolant cools here to a recuperator. So you don't send it all to the environment. Some heat rejection happens to the environment to establish the flow from the high temperature reservoir to the low temperature reservoir to establish the flow. But here, before you start heating the gas, you have to send it through a compressor, and then you add the heat inside the reactor, and you can add even more heat in that. First you add the heat from the recuperator as much as you can, and then you heat it inside the reactor. So in fact, today what we are using is only primarily, I would say, the Rankine or the steam turbine cycle. The Brayton cycle, which is the cycle for the future, is still in the experimental stage, pilot plant stage at different laboratories and universities, particularly in Japan and China, none in the United States. So this is a depiction of the two cycles, or a quick comparison on what we call the temperature entropy diagram. It's abbreviated in thermodynamics as the TS diagram. All right, so let us think now about what kind of thermal cycle. Remember, that energy extraction from the environment can be thermal, can be aerodynamic, wind turbines, it could be hydraulic, like dams and hydroelectric power. We are going to concentrate on the thermal power cycle. Most reactor designs today use the steam or the Rankine cycle that I have shown in a moment ago. The newer prospective designs take advantage of new developments in turbine technology. So for instance, new developments include using magnetic bearings, maglev, magnetic levitation. If you use a magnetic field instead of bearing rubbing against each other, then you reduce the friction and you can have high rotational rates for shafts of machinery in general. So with the use of Brayton gas turbine cycle, the gaseous coolant such as helium is enclosed in a single circuit, and its depressurization of leakage compared with water is minimized, and then you get a higher efficiency, and the high temperatures are usable for the production of hydrogen, either from electrolysis of the water using a DC current. You can separate the hydrogen from the oxygen, and the hydrogen in that case becomes like an energy storage medium. It becomes an energy carrier because you can move it from one spot to another after you store energy in producing it. So two important thermodynamic cycles, the Rankine or steam turbine cycle. This is the one that we are using today. The Brayton Joule or the gas turbine cycle, because of its high temperature, is on the drawing board. So that's something in our future as fossil fuels, dead plants and dead animals, where energy has been stored over 200 million years. We are using it at a rate of depleting it within 200 years. And in the process, we are causing our climate to change. If you read the news today, you'll find that dozens, literally dozens, have been dying, elderly, particularly in Canada, on the west side, on the west coast of the North America in general. But these are not the only cycles that we can consider for power production from the nucleus. Another process is, or a thermodynamic cycle, is called the Stirling cycle. This Stirling cycle was discovered or developed by Robert Stirling in 1886. This is called an external combustion engine. It differs from the Rankine cycle is that it uses a gas such as air, helium, or hydrogen instead of a liquid as its working fluid. And the working fluid is heated from the outside. So it lends itself to applications like solar energy production. So solar, if you concentrate the solar radiation at a point, you can use it to, in an external heat engine, the Stirling cycle, and it can have theoretically an efficiency that is equal to the ideal Carnot cycle efficiency in the thermal cycle. So in that case, a cycle would be ideal for a stealth nuclear submarine, since it eliminates the explosive pistons operation of diesel engines and the coolant pumping of steam engine systems. Ideally, it would also use magnetohydrodynamic propulsion and heat pipes for a vibrationless and bubble-less propulsion system. And the Swedes built a submarine basically that uses that Stirling engine, hence it is totally silent and can sink aircraft carriers without being detected. Another possible cycle that we can be envisioned, especially for space power applications, is what's called the dissociating gases cycle. Again, that was ideal for killer submarines, because in that case, you'll find that you can reduce the weight and the volume of the turbo machinery. So what is a dissociating gas? Some gases like nitrogen tetroxide, upon being heated, dissociate into two molecules of nitrogen dioxide. So here you start with one molecule of a gas and you heat it, you dissociate it into two molecules of the gas. And if you cool that nitrogen oxide, it turns back into nitrogen tetroxide. Now look at the ideal gas equation that describes the work done or the done per unit mass. It's equal to P, the pressure, multiplied into the specific volume, which is the inverse of the density. That's not volume, it's specific volume or density. You'll find that this is equal to nRT. R is a gas constant and T is a Kelvin degrees, if you want to call it. But once you turn one molecule into two molecules, that N in the ideal gas equation becomes twice N. So in that case, you are doubling the work done by the working fluid in the cycle that you are using. And there are different gases that can be used in that case. So one that I mentioned, the nitrogen tetroxide, has an increased factor in the gas constant of 2, with a temperature range that is meaningful, really, from 25 to 170 degrees Celsius. You can use also aluminum bromide. You can use aluminum chloride. All of these are dissociating gases. You could see here the gas constant 2, 2, 2. And you can even find gases like aluminum chromide plus liquid aluminum, where the increase in the gas constant is 6. So when you double the amount work per unit mass of the coolant, you can, in that case, produce a turbo machinery that is very compact in size. And we know that it's very costly to send into space any kind of equipment. So this idea lends itself not only to space applications, but also even to reducing the weight in an engine for, say, a killer submarine. I had a student who joined the Navy afterwards, work on a thesis where he tried using one of those cycles as an engine for a killer submarine. And of course, he found that he can increase the acceleration, hence the speed that can be reached by the nuclear submarine. If you have the same amount of power with less mass to move, you can reach much higher speeds. So it's a submarine that cannot be really followed. Example for the use of different working fluids is shown here. If you use like today's a water steam turbine with an output of 500 megawatt electric, let's compare this to a similar system using a gas turbine using aluminum chloride. Why aren't we using these today? Well, the technology is much more complicated and aluminum chloride is toxic. So we have to deal with the toxicity of those working fluids. But say that you have a 500 turbine using water or aluminum bromide. You'll find that you can produce the same amount of electricity. However, look here, the length of the turbine in the case of the water is 29 meters. The length of the turbine in the case of a dissociating gas, the aluminum bromide, is only 9 meters. So it's 1/3 the length of the turbine. It takes much less volume. It takes also much less weight. And what matters is really the weight. Well, then the weight of the turbine, of course, here would be 964 metric tons. 1 metric ton is 1,000 kilograms. This one is only 55. So if you take the ratio of the megawatt electric that you produce in your turbine per metric ton of the weight, in the case of water is 0.5, but then in the case of aluminum bromide is 10. So 10 divided into 0.5 is 20 times. So you get a 20 times really increase as a figure of merit in the energy, the power that you produce per unit mass. So in that case, you get very, very high accelerations and very high smaller volume in general. So it's a factor of 20 in the power to weight ratio. Think about the Volkswagen with a 2-cylinder engine compared to a Lamborghini car with an 8-cylinder engine, how fast the acceleration can be. So here we have 2 more cycles. The Stirling cycle as potential other than the steam turbine cycle that is used today. We already have the gas turbine cycle on the drawing boards. The Stirling cycle could be also another application, and the dissociating gas turbine cycle. That's not enough. There is another interesting cycle, the multi-fluid cycle, and it's designated as a Kalina cycle. Kalina is the name of the Russian scientist who came in from Russia, that his name was Kalina, and he came in and settled in Florida, and he applied the idea to geothermal energy production. Now, geothermal heat, as we covered in the one of the previous chapters, is low temperature system. So you really want to adapt it to a system that can operate at low temperatures. So Mr. Kalina came up with the idea of using a dual fluid cycle. So it is not just water as a coolant, but he added to it ammonia. And we all know ammonia, we use it for cleaning glass on our windshields in cars, or ceramics in our bathrooms. Ammonia has a very low boiling point, so it adapts itself to low temperature operations. So geothermal applications would be one good use. However, the fact is that you can increase the efficiency of the cycle tremendously. I had a student who worked on adapting the Kalina cycle to boiling water reactor, and the efficiency was increased in that case on an exergy basis by 30%. So that could be a cycle in our future. We look back at those cycles in more detail as we go along, but I want to point out that we don't have just one single system for producing heat energy from, well, in that case, fission, but you'll see also that that also applies to fusion as an energy source in our future. All right, so let's become a little more quantitative here by trying to carry out some calculations, design calculations. Most of the material I'll cover now, maybe you covered it already in your thermal classes, but for those who didn't have the chance, or those who forgot it, let us redefine the entropy. ds, differential in entropy, is equal to dq over T. This is a change in the heat addition divided into the absolute temperature in kelvins. If you can say ds is equal to dq over T, then delta S, or S2 minus S1, can be written as the integral of dq over T. So you can deduce from that equation that Q is equal to T, the integral of ds from 0.1 to 1.2 on the TS diagram. And first, if you have any thermal book, you'll find that in the back of it, there is some kind of a folder that contains a large chart. And this is called the Mollier chart. It shows the enthalpy against entropy diagram for different working fluids, primarily water, really, that we use as a cooling medium. So what is the enthalpy? The enthalpy is the total energy inherent in the working fluid. So this, we also can show what's called the temperature entropy diagram. So this is, follow the arrow here, you could see that there is a shape that reaches a maximum here and comes down. This is what's called the saturation line. And along the saturation line, you'll find that as you heat a fluid from this point to that point, you add latent heat to it until you reach here the point where you have the saturated steam. Then you can add heat to it following either the isobars, which are constant pressure lines, or the isotherms, which are constant pressure lines. In that area, you'll have a mixture of steam and water for a water system. On that side, you'd have only a liquid. On that side, it's all steam or a gas. And this is what we call the critical point. Above that point, the working fluid like water would be fully in the form of gas. We use that diagram for the design of thermal systems in general, the TS diagram, or the Mollier chart, which is now an enthalpy against entropy diagram. So this is again the saturation line. Each one of those lines shown here describes the degree by which the water has turned into steam. So at that point here, for instance, it's this is a quality line. 0.94 quality means 94% of the water has turned into steam. And when you reach the saturation line, it's now 1. So that is all the water has turned into steam. So the enthalpy is in thermodynamics defined as the flow energy, PV over J plus the internal energy. It's simpler in design application to use the combination of the flow energy and the internal energy. Again, U is the internal energy and PV over J, the Joule's constant, is the flow energy. All right, along this line, we can define now the different efficiencies of the different cycles. The ideal cycle in thermodynamics, obviously, is the Carnot cycle efficiency. And again, now the principles of energy conversion apply. You have to create a high temperature reservoir and establish a flow from the high temperature reservoir to the low temperature reservoir. Eventually, you get a net output from your engine, in that case, a steam turbine, divided by the heat input, and that defines the efficiency of the process. And it's our task as engineers to maximize that thermal efficiency, extract as much energy from the flow system and not just waste all our energy into the flow. It is not rejected here or wasted heat, it's energy needed to establish the flow, if you look at the perspective that we are presenting here today. What is the network done? You have to pump the fluid. So usually it's a difference between the work done in the turbine, the work that you get out of the turbine minus the work that you have to invest into running a pump to pump the fluid, divided by the heat that you are adding to the system. And in other words, it's really the difference between the heat addition minus the heat rejection, the net heat that you get as work, divided by your investment in the energy put into the process. In that case, we can think about the boiling water reactor, where you have a reactor core, you let fission occurs, so that is your Q sub A in the efficiency equation. The steam is produced, it goes to a turbine, that's a symbol for a turbine. It expands into a higher volume or a load specific volume, and the shaft of the turbine now is coupled to an electrical generator where we get the electricity. We have to close the cycle by taking the steam out of the turbine and condensing it back into fluid and using a pump to recirculate it into the reactor core. So that is what we call a condenser. It could use cooling towers or a body of water like a lake. If you think about the heat addition as being equal to the addition temperature multiplied into delta S on the TS diagram that we are going to show here, corresponding to that boiling water reactor design, you add the heat from at the temperature T1 in kelvins from 1.1 to 0.2 in the diagram. So this is what happens inside the reactor core from 1 to 2. Then 2 to 3 is 1 to 2, you add the heat, and now it's steam, it expands in the turbine from 2 to 3. So that is in the diagram, and it goes clockwise, as we know, 2 to 3 expansion in the turbine. Then you condense the fluid, so you reject heat to the environment at a lower temperature, and in that case, you have established the flow from a high temperature reservoir to a low temperature reservoir. What is the efficiency? It's really the heat addition, T delta S. This is a change in entropy on the TS diagram, and minus the heat that you have basically sacrificed to the environment to establish the flow. The difference is that area here of the square, the hatched area, and that is the work done in your device, and we want to maximize that value, obviously. But the Carnot cycle efficiency then becomes, if you substitute in the heat addition expression as delta S into T, the areas of the rectangles, you find that the Carnot cycle efficiency can be written as the heat addition temperature minus the rejection temperature divided into the heat addition, which is the same as 1 minus T of the fluid, the working fluid, divided into the heat addition temperature, T sub A here, and the rejection temperature here would be T rejection, or TF. Notice that the efficiency must be less than 1. And notice, please, also that when you apply the efficiency equation, I repeated, and because many students still in tests or exams, or hopefully not in the workplace, mistake that T here as being the Celsius temperature. Is not the Celsius temperature. This is a thermodynamics law, and T here is in Kelvins, 273 plus degrees Celsius. All right, so that represents the boiling water reactor. How about the pressurized water reactor? The pressurized water reactors does not produce steam in the core of the reactor. So if we show the cycle diagram for a pressurized water reactor, you'll find that you pump the water into the core, but do not allow it to boil. So in that case, you find that the water remains in its liquid state. You take it into a steam generator, or you bring in water into the steam generator, and you allow the water there to boil, then take it to the turbine and then to a condenser, and then heat up the water as you return it back to increase the efficiency. You'll find here then that we have two temperatures, the heat addition at T sub A, and the heat in the steam generator at T1. So there is some kind of an inefficiency here. The same when you pump the fluid from the condenser through the feed water heater. When you add the heat, you start here when the liquid is fully a liquid at 0.4 in the steam generator. You keep adding the latent heat until you produce fully steam out of the steam generator. You take it to a turbine at 0.1. You expand it from 1 to 2. Here on the two diagrams correspond to each other. And then from 2 to 3, you condense it, and then you pump it through the pump from 3 to B here. 3 and B are very close to each other, so it just adds some heat through the turbulence in the pump, and then you start adding the heat here in the steam generator, the Q addition, and the heat of vaporization in general. So in that case, we can write for the efficiency of the Rankine cycle, the regenerative in that case, in terms of the enthalpy now, is the work done in the turbine, which is the enthalpy at 0.1 minus enthalpy at 0.2, the total energy, if you want to call it, minus the heat done in the pump from the enthalpy at B minus the enthalpy at 3, divided into the total heat addition for the enthalpy from 1.1 here, point H1, minus the enthalpy at B. So the B here and the H3 are very close to each other. So in that case, that term cancels. And we can write for the pressurized water reactor cycle that the Rankine cycle efficiency is the enthalpy at 1 minus the enthalpy at 2. Here, the work that you get from the expansion of the steam in the turbine divided into the heat addition from the enthalpy at H1 minus the enthalpy at H3, because B and 3 here are very close to each other as a simplification of the process. So the Rankine efficiency for the PWR is the enthalpy at 1 minus the enthalpy at 2 divided by the enthalpy at 1 minus the enthalpy at 3. How do we carry out the design of such a system? Oh, we go either to the steam tables or use a Molière chart. So we choose maybe a operating pressure and operating temperatures, the two line on the enthalpy S against entropy diagram, which is a Molière chart. This could be 0.1. Then we say, okay, that's a point that we are using for the temperature of our steam, and we expand it in the turbine from, say, a pressure P1 to a pressure P2, and then we follow the line of constant pressure, and basically by trial and error, we design the turbine and the electrical generator in general. All right, as engineers, of course, we want to minimize the energy that is used in establishing the flow, which in thermodynamics books is called the rejection energy. It's not rejected, it's a flow. From our perspective, it's really more like the flow energy. So in that case, suppose that we take a TS diagram here, and we use a cycle in which we are adding the heat from 1 to 2, and then adding, this is a heat addition to heat the liquid in the core of the reactor. Then we use the latent heat of vaporization up to the saturation line, where the water becomes fully steam, expanded in the turbine, and then condense it back to 1. Now, how do we increase that efficiency? We increase the efficiency by maximizing that area in that parallelopiped, or call it, or rectangular shape, maximize it as much as we can. So we can maximize that area here by decreasing the temperature at which we are rejecting the heat. So instead of rejecting at a temperature 1, we reject it at temperature 1 prime. But we don't have control on the environment, really. We cannot cool the environment. So you'll find that that increase in the efficiency depends more on the geographic location where you build your power plant. So if you have a power plant operating in Florida, where the temperature rejection to the environment is higher than, say, a power plant operating in Canada, where the temperature would in principle be lower, except for the last week, where it's higher than the continental United States. But basically, that rejection of the temperature depends on the environment. It depends on also on the weather conditions, like our engines in that case, we can tell, would operate at a higher efficiency. You get a higher rectangle here in the winter than in the summer, where the rejection temperature is lower. So enhancing the efficiency depends really on the location, or depends on the season when it comes to decreasing the temperature, rejection temperature. Okay, how can we then increase the efficiency or maximize that area? Let's try to do something else. Let's increase the temperature at which we are adding the heat. That's Q addition here. And let's assume that we remain at the saturation line. So in that case, if you operate at that temperature here, this is the net work that you get. If you operate at that higher temperature, this is the net work that you get. And it's a trial and error, really, on the Molière chart. It depends also on the materials that we are using. Are we using ceramics for the blades of the turbine, or are we using aluminum or steel? This is basically not necessarily a way of enhancing the efficiency, because that area here can be larger. The area operating at a lower temperature for heat addition could be better than operating at an even higher temperature. If you only increase the area by going to a higher temperature. The real increase in the efficiency can come in if you, without having to go to very high temperatures like here, by operating at low temperature, adding the heat at low temperature, but then once we reach the saturation line, we follow a constant pressure line or a constant temperature line isotherm and superheat the system. So in that case, this is a hope for you to get a higher efficiency in your cycle than just operating at a given temperature by superheating. So superheating is a way of enhancing the efficiency. In practice, in operating nuclear power plants on the steam cycle, we use a two-stage regenerative Rankine cycle shown in that diagram. So why is it two-stage? Let's assume we are using a pressurized water reactor. We generate the steam. We heat the liquid after pumping it into the core. The liquid goes into a steam generator where water comes in from feed water heaters, turned into steam and gone to a turbine to the electrical generator. The regenerative process tries to enhance the efficiency or decrease the amount that we have to devote to the flow system by bleeding steam as it expands through the turbine. So at that point here, if you have a mass flow rate m dot of steam going through the turbine, you come in here and bleed some steam, an amount m1 dot, mass flow rate, kilograms per second, send it to a feed water heater where the water coming from the condenser now is heated, it is condensed and led into the previous stage of another feed water heater. That's why it's called a two-stage regenerative cycle. In that spot here, you can add what's called a steam trap so that the steam does not, the liquid, the steam that is condensed as a liquid is added to the previous stage as a liquid. So in that case, the second stage uses another mass flow rate of the steam expanding in the turbine. You'll see that, of course, what's left is m dot, the initial flow rate going to through the steam generators, minus the m1 dot bled to the first stage feed water heater, minus m2 dot, the steam going to the second feed water heater. That m dot minus m1 dot minus m2 dot flow goes to the condenser and to the hot well of the condenser. And then as the condensation of m1 dot here and m2 dot here join out, you'll find that in the hot well, you are back to m dot minus m1 dot minus m2 dot plus again the m1 dot plus m2 dots. Or you are back to the m dot flow that goes back into the steam generator. By adding this complication here, we are using some of the heat that is used in the flow system in a more efficient way. So, but the expression for the efficiency becomes much more complicated. So in that case, you can find that the work in the turbine is the mass flow rate m dot with a change in enthalpy H1 minus H2, plus another amount m dot minus m1 dot by changing enthalpy H2 minus H3, plus another mass flow rate m dot minus m1 dot minus m2 dot by changing enthalpy H3 minus H4. So this is the work done in the turbine. And if you divide that into the heat addition to the cycle, which is m dot H1 minus H2, you can get the expression for the eta for the regenerative cycle. And hopefully it's as close as possible to the Carnot or the ideal cycle efficiency. So this is really what we use in existing power plants, whether it's nuclear or coal power plants. The regenerative cycle is almost universally used, using water as a coolant. In our future, we are thinking about the gas turbine or the Brayton cycle. So I provide you here with an analysis. The cycle would be very different when you use a nuclear power plant. So you assume that you are using a gas-cooled power plant now. The flow of the helium or the gas coolant carbon dioxide goes through the core. Heat is added to it. Then the gas goes to a turbine and expands, producing electricity. Now we can use some of that electricity to pump the gas into the system, but electricity is an expensive form of energy because it went through the conversion process from heat to mechanical energy to electrical energy. So in that case, instead of using electricity to pump the working fluid, we place a compressor that will circulate, or a circulator for the air, or a blower, if you want to call it, along the same shaft as the turbine. So typical of the Brayton cycle or the gas turbine cycle is that you have a compressor on the same shaft as the turbine going to the electrical generator. You have a cooler here. In that cooler, you reject the heat to the environment to create the flow system. The cycle here, if you look at 1 to 2, it's compression. 2 to 3, it's heat addition. 3 to 4 is expansion of the turbine. 4 to 1, this is a simple ideal cycle that can be shown either on the TS diagram. 3 to 4 expansion, isotropically, meaning at constant entropy. Usually it is not really in real life a straight line. It comes out with some inefficiency at the point here, at that point. But 3 to 4 is expansion. 4 to 1 is heat rejection. 1 to 2 is compression. 2 to 3 is heat addition. You can put this also on the PV diagram, pressure and specific volume. And the area here is really divided by the total area under that graph here from the Q addition is the efficiency of the cycle. We can do this, but in a gas turbine, I don't have a diagram of a turbine that would be used with water as a working fluid. But if you drive by Tilton on the way to Danville, you'll find that on the north side of the highway, there is a gas turbine kind of site. A gas turbine that is used in that case used the compressor on the same shaft as really the turbine itself, but in that case, the working fluid is not the carbon dioxide from a nuclear power station or the helium, but they use natural gas, and that's the name of a gas turbine. So this is what's called an open cycle gas turbine. The exhaust there is simply exhausted to the air. In a combined cycle gas turbine, the exhaust here is taken back to a steam cycle, and that's called the combined cycle gas turbines. But typical of a gas turbine is that the compressor and the turbine are on the same shaft. This is also used in the engine turbojet aircraft. I'll show you the efficiency in that case in terms of the enthalpy, and if you find yourself designing one of those systems, you'll find that the derivations here can be used in an archival way. What is the best gas to use in a gas turbine or in a gas high temperature gas cooled reactor? You could see that ideally you would use hydrogen. However, we know that hydrogen is highly reactive, so it's only used in special applications. Hydrogen used, for instance, in the cooling of the winding on electrical generators, even though it's very reactive with air. If there is a hydrogen leak, it can cause an explosion. And that has to do with its specific heat. It has a specific heat of 3.4 British thermal units BTU per pound per degree Fahrenheit. So because it's hazardous, basically we can substitute for it helium. Helium has a lower specific heat, 1.25, compared with hydrogen, but it is not reactive. It's a noble gas, so chemically stable. Carbon dioxide with a much lower specific heat was also used. That's 0.2 BTU per pound degrees Fahrenheit. Now we know that helium, we have a shortage of helium. Well, helium is used in birthday balloons, for instance, but it's also used in a cryogenic way to operate our nuclear magnetic resonance in creating cryogenic kind of conductor superconductivity. So we might basically not be able in the future to use helium. A substitute for it would be maybe nitrogen. And we know that the air we breathe is 70% nitrogen. And if you can allow oxygen to get into your device, which would cause corrosion, you can simply use air as a coolant. The specific heat is not different much from nitrogen because nitrogen is really 70% of the air we breathe. The equations are listed here archivally. We're not going to use them, but if you design in the future a gas-cooled system, this is a way of calculating the optimal pressure ratio in the gas turbine. And I don't want to turn our class into a thermal class. We want to look at different reactor concepts in general. There is an optimal thermal efficiency of the Brayton cycle that determines the compression ratio. So the optimal gas temperature after compression, the combination of the compressor and the turbine blades is, of course, has to be optimized in general. So, so we dealt here in more detail with the steam cycle and the gas turbine cycle, but one very promising cycle for our future is the Stirling cycle, especially as an external heat engine application for solar application, but also if you have a radioactive isotope producing heat, you can use the Stirling cycle. And the Stirling cycle in that case is applicable to the future space reactor. So it's of great interest to our aerospace engineers taking our class, in that you can use a fission product or a fission process to heat a working fluid like sodium, and in that case, you don't need turbo machinery, you don't need rotating machinery in space. So only the fluid circulates on the working fluid, heating an engine from the outside. And that shows us the process of energy regeneration in a typical Stirling energy that's using fins here to exchange the heat. And as you could see here, you have a piston inside the engine with a temperature difference being heated from the outside. As you heat the engine from the outside, it goes down, up and down. You cool it by rejecting the heat on the outside of the turbine. When you create that linear motion up and down, and you move a coil inside the magnetic field, oh, you get an electric current out of it. So it can be applied very easily to nuclear energy. And in fact, it is used as a possible replacement for in radioisotope power generation. If you use a Stirling cycle, you find that on the PV diagram and the TS diagram, if your QR here, the rejection of the heat here is added exactly here through a regenerator, you can get a cycle efficiency for the Stirling cycle that is the same here, I prove it to you, as the ideal efficiency, the Carnot cycle efficiency. So we find that the attempt efficiency is basically interchangeable. I'll give you a problem about the space application for the Stirling engine. In fact, you find here that research is being conducted maybe at the NASA Glenn Research Center for replacing the thermoelectric power generators that we covered in the chapter on power production from radioactive isotopes. There are still used radioactive isotopes here in the center part. In that case, you heat up the working fluid, you get a piston moving back and forth, and in space, there is no medium to use convection for cooling. So you could see here those fins act as a way to reject the heat into space. Now, you don't want linear motion back and forth to start getting a reaction on the aircraft. It would start also moving in the opposite direction. So you cancel the linear motion by having two basically pistons moving back and forth in opposition to each other. So they cancel the linear momentum in that case. So this is replacing now the thermoelectric generators that NASA is using. And this is an actual device developed at the NASA Glenn Center, so to produce electricity from radioactive isotopes for space applications. As I suggested, look at the efficiency that you can reach, especially because the temperature of space is very low. You can get minus 40 degrees Celsius in space, and the hot temperature from the radioactive isotope can be in the range of basically 650 degrees Celsius. So if you take the Stirling cycle efficiency, which is the same as the cycle efficiency for the Carnot cycle, if you heat up your element, the hot part, to 650 degrees Celsius, and you have a rejection, the cold temperature to space is 120 degrees plus 273, that's a Kelvin degrees. You look at the efficiency that you can reach. You can reach about 60% efficiency compared to 30% efficiency for light water and boiling water reactors. So the Stirling cycle is a very, very promising cycle for future applications. I mentioned the Kalina cycle, and this is a dual fluid engine cycle. So we go over it also in some more detail here. The cycle becomes quite complicated because you have now two fluids that have their own heat rejection and cooling cycle. If you are interested, you may look at it in more detail. This is the cycle diagram, but let's look very quickly about what kind of an advantage do we get if we apply the Kalina cycle. If you use the Rankine cycle, you would have a working fluid like steam as a gas. It operates at maybe between 550 degrees Celsius and 400 degrees Celsius. In that case, the working fluid is a gas cooling the reactor, and then you bring in the steam operating at 500 pounds per square inch. And this is the range of the energy recovery process. You can get an energy recovery, maybe let's call this one. If you use a Kalina cycle, now you still have a gas, but the fact that you are using a mixture of water that produces steam and ammonia, 70% ammonia and 30% water, allows you to have a much larger range for the exchange of the temperatures. So you can go in the exchange process of the gas from 500 degrees Fahrenheit all the way to 200 degrees Fahrenheit. So basically you find that the energy recovery is doubled or even maybe 2.5 times what you get from the Rankine cycle. So this is another cycle for our future in general. I'll give you two problems to work on for today. You are responsible for what we'll cover today for the test that will be given on Friday. And I'll stop sharing here and answer any questions in